What is going on, ladies and gentlemen? It is Jake coming at you with another video where we're talking about computer science. Today, I wanted to start a little mini-series talking about the fundamentals of computer science, the fundamentals of IT in general, and make, I guess, mini videos here and there, short videos, talking about a general topic. This being the first video of that series, where do we begin? I think there's always been like a saying where, machines read ones and zeros, that's all they understand, which is in fact correct. I'm sure you've heard it. But let's elaborate in this first video a little bit about what that means. We're talking about binary numbers, and so let's jump into it. So when we talk about binary and decimal numbers, what we're really talking about is a way of representing data in front of us. At its core, we use numbers for counting, for math, for representing abstract things, and it's what made the world around us. It's a beautiful thing. But we have a set of 10 digits to use, while in binary we only have a set of 2 digits to use. So why the description? Well, I want to say, don't take my word for it, but I think we have a set of 10 in decimal because we have 10 fingers, or we have 10 toes. Like 10 just makes sense for us humans more than, say 8 or 9 or 15 digits counting wise. I think there's some ancient civilizations that had some crazy number systems out there, but we're sitting here on the decimal system at 10 numbers to use. And for binary numbers, we only have a 0 and a 1. Why is this? Well, it is, at its fundamentals, electricity. I know you have a smartphone, I know you have a computer, and it might seem like it's all magic, but it is in fact, at its core, still, these circuits, these registers, and these waves that can either be low or high. So, a value in a circuit can only be 0, as in low frequency, or 1 being high frequency. You wouldn't want to have like a medium, or there's a lot of, you could imagine you could have like maybe 4 numbers being like a low, a medium, high, and then a really high. But with the amount of data that's moving, and there's so much fluidity in the voltage, you would want to just have a 0 or a 1 for I guess to not corrupt your data. If you had, a couple layers in there, like we could represent 0, 1, 2, 3, 4 with like different layers of voltage, it could get, a little messed up. There could be some corrupt bits in there, and you wouldn't want to be on your iPhone, and then all of a sudden it just like explodes. It wouldn't explode, it would crash. But that is at its fundamental why we have a 0 and a 1. So a high voltage and a low voltage, you can imagine what that is. So when it comes to representing these numbers, obviously when we're counting, we count with 1, and we go up to 9, and then we say 10. And when we say 10, we actually, carry over our bit and start over again. And so we do that all the way up to 99, and then we start with 100. And we do that all the way up to 999, and then we go to 1,000. And so the same system is going to work when we're talking about binary numbers. I put some zeros here so that way we're not like confusing ourselves, because they do look the exact same. And so we're going to start at this 1, and let me slide this guy over here. So we start at 1, and this 1 can represent either a 0 or a 1. That's all it is. I mean, it's the first bit. It's kind of like here, you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all you can represent. But then we get here, and I can add another 1. So that would be 2. So we're talking about this place is going to be our 2's spot. Okay, and so with that I can represent 2, and I could represent 3 if I had, a 1 and a 1. Kind of like here where if I have 10, if I had, let's say, like a 2, I would be 2 plus 10. Here it's kind of like 2 plus 1, and that's 3. You could think of this as 10 plus 2, or you could think of it like if I had the number 998. Technically it's 8 plus 90 plus 900, kind of the same deal over here. And so what's after 3? Well, we have 4. And so with 4, I can represent 5, 6, and 7 with, these bits over here. And eventually we're going to get to 8. And with 8, I can represent 9, 10, 11, and then 12, 13, 14, 15, 16. We won't be able to get to 16 over here. And if you can't find the pattern yet, what's going on here? So we have, I guess, like 2 to the k, where k is that, I guess, element in the index that we're at. So this would be k of 0, and we can just go over here. So we got like kind of like a 0, and we got a 1, and we got a 2, and I'm trying to map these to these registers over here, jumping over these numbers like so. And we can kind of, you know, see how this guy is 2 to the 1, it's 2, 2 to the 2 is 4, 2 to the 3 is 8, and so we kind of just add numbers as we go. Simple enough, right? It is an interesting concept, because essentially what we're doing is, instead of having 10s, we only have 2s, and the 2s go in exponential form, going upwards. And so if we scroll down here, how would we represent the number 13 in binary? So here we just have a couple of bits over here going from 1 to 32. So we have our 1s place, our 2s spot, our 4s, yada yada yada. And when it comes to representing decimal numbers, and usually what we actually do is put a little 10 down here. So now this is base 10. We're talking about a base 10 number. How would I represent that in a base 2 in a decimal number? My way of doing it, I don't know if it's the best way. There's probably like a better formula for doing this, but just intuitively, what I like to do is write out my numbers and what is the biggest value that can go into 13. 32 will not go into 13, 16 will not go into 13, but 8 will. So we'll just subtract 8 down here, and what do we get? We get 5 back. Okay, that's fine. And so which number that we have now, what number do we have now that can go into 5? And you can kind of see we don't have to look at these numbers anymore. We can just look at 4, 2, and 1. And 4 does indeed go into 5, so we'll just minus 4. And we get a 1. And so a 2 doesn't go into a 1, but a 1 goes into a 1. And so then we get 0. And we get our number back. And this is how you would actually represent a 13 in decimal form. We essentially just, you know, minused all the remainders out, kind of like doing some crazy subtraction, and we get a 1 plus a 4 plus a 8, which is in fact 13. So you might be thinking to yourself, Jake, that is so cool. Oh my gosh, I can now interpret, you know, decimal numbers into binary numbers. Mind blown. But no, there is so much more to it than that. I mean, I'm talking to you through a video on YouTube right now, which at its core is all 0s and 1s. So how is that possible from this simple concept? I would have to thank the computer scientists that came before us and all the programmers that, like, in the 60s all the way up to, you know, the internet age, because they came together and they said, let's make some standards. Let's make some assumptions and document like what these values are going to mean. When I'm representing color, for example, I think it's kind of a well-known fact that it's 0 to 255 on the red and the green and the blue. Kind of like when we look at a color wheel here, you might be familiar with the hex of like 00, FFF or something like that, and this would make a color. But essentially what this means is the computer knows if I'm looking at a color, it will see that it's a color object that it needs to interpret, and the way that it knows that it's a color object is in itself something special that we can dive into in a different video. But, you know, it knows that 8 bits can make up 255, like the maximum values, that 255 number, which is at most 8 bits. And so by having three 8-bit numbers in a sequence together in a row, the computer can represent that color. And so here for our reds, there's nothing but 0s. For our greens, there's nothing but 1s. And for our blues, there's nothing but 1s. The computer sees this as a just stream of 24 1s and 0s, but with special interpretation in our compiler, it will know that it is cyan. It is cyan color. And one quick concept before I let y'all go is this idea of the hamburger concept. And yes, we're gonna make a nice Krabby Patty real quick. When we use computers, when we use and write code, we're really doing it at this meat level. This is, you know, the meat. We are in the middle. But on the opposite ends, when it comes to using a computer, when it comes to using the device, there are these buns that are being used that we simply just don't need to worry about. And this is the binary data that's coming in. Binary in. And this is the binary that comes out. So every single time you pick up a device, every time you write some code, essentially what is coming into your program is a binary number. When you're typing on your keyboard, you know, like A, B, C, D, all that jazz, there's like a wall. There's like, you know, we can only see light, and we can only smell, and we can only taste, but we can't see, like, you know, the RF waves around us in life. And just when we're computing, or when we're on the computer, we don't see the binary that is at work. We only deal with the meat, but each action you do is always going to have some binary in and some binary out. But guys and ladies, that was this first video talking about binary nodes. I hope you enjoyed. Hope you learned something new. I hope my crazy analogies made you laugh, or, you know, made it a more enjoyable experience. And until the next time, peace.